Hello there. We're going to go over a few example thermo problems today. I've put here an old exam from fall of 2017 in the OneNote notebook. I'll also show you that I've added the appendix from the OneNote notebook where we have all our thermodynamic properties here. That's another tab in the OneNote notebook there now. But let's look at some of these problems and I'll show you how to work them. Okay, so we're start off here with a problem where we're looking at the reaction here that we've got sodium nitrate and sulfuric acid reacting to produce nitric acid and sodium bisulfate, and we're asked to calculate delta H for this reaction. Again, so this is a review question from back in Chem 131. Delta H for the reaction is going to be equal to the sum over the products of the delta H formation multiplied by the coefficients, and then we're going to subtract from that the sum over the reactants multiplying by the coefficient delta H sub F for those. So in this case, what we're going to have is we're going to have the delta H sub F of the ammonium bisulfate. That's our first product, and we're going to add that a sum, right? Sum of the delta H sub F of the nitric acid. And I'm not writing the states here, but those are important. And then we're going to subtract from that the sum, which I'll put in big brackets here, of the delta H sub F of the sodium nitrate. And then we're add to that the delta H sub F of the sulfuric acid. And again, I haven't paid attention to the states here, but it is usually important to do that. Now, this is really not that hard. You just have to keep your signs and all straight. So NaHSO4 is negative 1125.5. So I'll write here negative 1125.5. We'll leave the units out. We'll take care of that at the end. Everything's kilojoules per mole. We don't have to multiply that by anything because the coefficient's 1. Then we need the delta H sub F of nitric acid. That's negative 135.1. And then over on the reactant side, the sodium nitrate is negative 467.8. And finally, the sulfuric acid is negative 814.0. And everything is in kilojoules per mole. So just a little arithmetic here. You can kind of ballpark the first term is going to be around negative 1250, and the second term is going to be around negative 1280 or so. So with the negative sign in the middle, I think this is going to be a little positive, maybe positive 20 or 30 kilojoules. Let's plug it in the calculator and see. Again, the main problem here is just making sure that you enter things in properly and you keep your signs straight. And again, it's a lot simpler when everything's being multiplied by 1. Otherwise, you have to take a little bit more care. The answer I get with this is that delta H for this reaction is, I get 21.2, and that's positive 21.2 kilojoules per mole is my calculated value. So that would be answer E, and the answers are at the end of this, so you can check that and see if I got that. So that's getting a delta H from the tabulated enthalpies of formation. In the case of the second problem, that arrow is in the wrong place. We have here and I guess we're going to have to assume these bond energies go this way. Looks consistent with what we have, so that didn't print out very well either. What we're doing here is we're estimating delta H using the bond dissociation enthalpies, or the bond energies. We have to think about Lewis dot structures a little bit to do this, so our acetylene is this, and then we got our two hydrogens, and I'll draw them both out, and then our ethane looks like this. Not too complicated, but it does require you to go back and look at that. So the equation here is that the delta H of the reaction is approximately equal to the sum of the bond dissociation enthalpies for the bonds broken, because we have to put energy in to break the bonds. And then we're going to subtract from that the bond dissociation enthalpies of the bonds formed. And so you can kind of cut this up how you want to. I guess what I'm going to do is get the highlighter here maybe, and let's highlight the bonds that are being broken. So we're breaking a triple bond between the carbon. We're breaking these hydrogen-hydrogen bonds right here. And then let's do in blue the bonds that we're forming that are new. The triple bond is being replaced by a single bond, and we're forming 4 new carbon-hydrogen bonds in blue there. So that can be how we think of this. So the ones broken, we're going to carbon triple bond, that's going to be, assume that's that one, 839 kilojoules per mole. And then we've got 2 hydrogens, that's going to be 2 times 432 for our broken side. So if I do the math for that, that's going to be something around 1700, I think. So I'll do 432 times 2 plus 839, 1700, I'm sorry, 1703 kilojoules. And then we're going to subtract from that the ones that we're forming. So we're forming a carbon-carbon single bond, that's 347. And we're doing 4 carbon-hydrogen bonds. Those are, so 4 times 413. So that's going to be close to 2,000, I think. So 4 times 413 plus 347 comes up to be 1999. And if I subtract that from my 1703, I'm going to get about 300, negative 296 kilojoules per mole is our estimate of that one. So that would be C, would be the answer for that one. Now question 3 here is asking you to describe processes as being spontaneous, and this kind of relies on your having some experience with these substances, which is not always a good way to ask a question, because everybody doesn't grow up playing with a chemistry set or anything, but you probably can think about these. So the first answer asks us if water will spontaneous, and of course when we say spontaneous, what we mean by that is thermodynamically favorable. That means delta G is going to be less than 0, but we're not actually going to calculate delta G's for most of these, although we could go to the tables and do that. Does water, even in the gas phase, does it break apart to form hydrogen and oxygen spontaneously? And the answer to that is that no, that does not happen. And we could go calculate it, I guess, and support that. They probably should have specified temperatures and pressure, but that's not the case. graphite going to diamond. If you take your pencil lead, which is graphite, and sit it out, does it turn into a diamond? Unfortunately, no. So we have to can't sell our pencil leads for the price of diamonds, unfortunately. So that's not spontaneous. Solid CO2 is what's known as dry ice, and you may have experience with dry ice. The dry ice sublimes and will do so at 0 C. So that's a spontaneous one based on experience. The second one is liquid water going to solid water, that is freezing at 25 Celsius, which is 77 Fahrenheit roughly, and that doesn't happen. Ice cubes don't spontaneously form in our drinks, so I would go with C as the correct answer for this. Again, we could have gone and calculated delta G and delta S from the tables and calculated our delta H and delta S and calculated delta G to look at these, although we don't have the tables necessarily for the temperature values. Most of the tables are at 25. All right. Number 4 here, we're asked to estimate delta S. So what we're doing here is we're saying that the delta S, the sign of delta S, is going to be proportional to the change in the moles of gas. So that's going to be the sum of the moles of gas for the products minus the sum of the moles of gas for the reactants. And if we look at our reaction here, we have no product moles of gas, and we have one reactant mole of gas, the Cl2. So that's -1. That's our delta N sub G value, so this suggests that delta S will probably be less than 0. So that's going to be answer D. Question 5 asks us to calculate the entropy change using the standard molar entropies, and again the delta S for the reaction is going to be equal to the sum for the products of the standard molar entropies times their coefficients, and then we have the sum of the standard molar entropies times their coefficients for the reactants, and that is not a plus in there, it's a minus that we're subtracting those. So we're going to have our delta S is going to be equal to 2 times the standard molar enthalpy of magnesium chloride solid. That's not a square bracket, but a curved one, parentheses, plus 1 times the standard molar entropy of silicon solid. And that's the products, and then we're going to have the standard molar entropy of silicon chloride, and that's times 1, that's in the gas phase, and then 2 times the standard molar entropy of magnesium solid. So we take our values here and put them where we need. So magnesium chloride, that's 2 times 89.62. And then silicon is 18.83. And silicon tetrachloride is 330.73. And then we have 2 times 32.68 for solid magnesium. And these are all in joules per Kelvin times mole. Notice that it's joules, not kilojoules here. So if I estimate here, the products are going to be about 200. 2 times 89 is pretty much 2 times 90. That's 180. 18.83 is about 20. So about 200 there. Then on the reactants, we've got about 400. So I'm thinking it's going to be around negative 200 something. So maybe leading towards answer A. Let's do the math. So our delta S, we plug it in the calculator. Again, you just have to keep your signs and your order of operations clear. You have to type the right number in. I just missed the 9 there, and it typed 86.2. Okay, so use your parentheses to help you deal with something. So 2 times 32.68 is going in a parentheses. And so what I come out here, as I expected, was negative 198.02 joules per mole Kelvin, or joules per Kelvin, as it's written in the answer. So that's answer A. Their logic of leaving moles out there is that we multiplied every one of these was moles, and this would be 1 mole times. So their logic is we cancel the moles out that way. So, but that's the value we get for that. I'm going to skip 6, which is a similar problem. Let's talk about 7. For a chemical reaction to be spontaneous only at low temperatures, which of the following conditions must be met? So remember, we talked about delta G is equal to delta H minus T delta S. And for spontaneous, again, we mean thermodynamically favorable. Delta G less than 0, right? Temperature is always positive, so our possibilities are if delta H is can either be positive, delta S can be positive or negative. Put our signs in here, and if delta H is negative, we can subtract that from this is positive. Positive temperature times positive delta S, or positive temperature times negative delta S. All right. So what we're looking for is something where at high temperatures the thing is going to be non-spontaneous. So what that means is that this whole term, this TDS term, has to be positive. And when the T gets bigger, that becomes more important and outweighs the delta H, which the delta H must be negative. So to get this whole term to be positive, positive times a negative is negative, minus a negative is positive, right? So that whole term together is positive, and then with the delta H being negative, that means that's going to be the one, if we go back to our graph, where delta G is on this axis, 0 is there, this is temperature. We start off down here, and it goes up in that direction as temperature increases, and that is the low temperature one. So this is the low one, and again that's delta H negative, delta S negative for that one. So you kind of remember that graph to analyze these. Okay, so here's one where we're being given some data of delta H of F and standard molar entropies, and we're being asked to calculate delta G. And again, this is my preference for you in terms of calculating delta G's, rather than using something like a delta G sub F, which I think is only good at one temperature and one. So that's why I don't want you to do that. All right, so let's do the delta H part of this. Delta H is going to be products minus reactants. So I'm going to say SOCl2 is negative 212.5. Cl2O is 80.3. Kind of cutting to the chase on this one. And then the products, we got 2 Cl2s, that's 0, so 2 times 0. And then we've got SO2, which is negative 296.8. So again, what we've got here, this is our SOCl2, this is our Cl2O, this is our Cl2, or 2Cl2, and this is our SO2 value there, and that's the delta H sub F's. And so estimating that the reactants, the products term, is going to be around negative 130, and then the minus the reactants term is going to be around positive 300. So I'm thinking we're going to have something like positive 170 for this. Let's see what we get. 112.5. It's 80.3, and then subtracting from that 296.8, which is negative. Oops, I think I've botched it. Let's try that again. 212.5 negative plus 80.3. And then I'm adding 296.8 negative and negative adds that. So 164.6, and that's kilojoules per mole. And again, that is a positive. That's endothermic. Our delta S value, we're going to take our standard molar entropy. So SOCl2 is 309.77. Cl2O is 266.1. Cl2 is 223. We got to multiply that by 2. And SO2 is 248.1. So same elements. Notice that the units here are joules per mole Kelvin. Notice that the element in standard state, chlorine, has a 0 delta H sub F by definition. Its standard molar entropy is definitely not 0, though, so you can't assume anything's a 0 on standard molar entropy. So let's look at this. The product side, we're looking there at about 575. On the reactant side, well, the first part's going to be about 450. It's about 700. So product side, what did I say, 775 minus about 700, so about 75. Looks like it'll be positive. Let's see what we get. 309.77 plus 266.1 minus parentheses 2 times 223 close paren minus now the 248.1. And that comes out to negative 118.23. Now, I've got my delta H and my delta S. To get my delta G at 298, I'm going to use delta G is equal to delta H minus T delta S. So that's going to be 164.6 kilojoules per mole minus 298 Kelvin, the temperature we're given, times negative 118.23 joules per mole Kelvin. That's going to take care of the kelvins, but I need kilojoules here, so I'm also going to have to multiply by 1 kilojoule over 1,000 joules to make this work out. That'll cancel out my joules, and then I'll be adding kilojoules per mole to kilojoules per mole, well, subtracting in this case. All right, so that part of it, I'm going to do that. So what I wind up with here is 164.6 minus the term I get in the parentheses is negative 35. I'll call it negative 35.2, rounded off, and those are kilojoules per mole. And so our final answer for delta G is going to be something around 130, 129. It's going to be positive 129.4 kilojoules per mole is my delta G that I've calculated here. So that's this guy right here, 129.3 is where they rounded that one. Looking at number 9 here, we're given our delta S, our delta H, and our delta G at 298. We're asked to calculate delta G at 900. What we're going to do there is use the same equation. Delta G is delta H minus T delta S. We're going to use the delta H's and the delta S's. So 169.4 kilojoules plus minus is kilojoules, minus our 900 Kelvin times our 78.1 joules per Kelvin times, again, 1 kilojoule over 1,000 joules So this whole part here is the T delta S part. So what we're assuming is that delta H and delta S don't change too much over that temperature range. The delta G is going to change quite a bit. So let's see what that value comes out to be. So I have 900 times 78.1 times 1 divided by 1,000. So what I wind up with here is 169.4, sorry, minus 70.29. That's all kilojoules. So that's going to be something around 90, I guess. Yeah, it comes out to be 99.11 is what I get. And so that's answer A for that one. So again, notice how much the 900 degree versus the 298 Kelvin, 900 Kelvin versus 298 Kelvin. See how different those values are. That's why I don't like using the delta G sub F. So 10 is kind of like this. I'm not going to go through this whole thing, but you don't want to use the delta G sub F's in this one. 9 was kind of a hint that you don't want to use that there. You want to calculate your delta H and your delta S, and then use those in the delta G expression for the 550 Kelvin. And I'll post the key to this exam so you can look at the answer to that one. This figure obviously did not make it through, so I won't say anything about this one, number 11, but you'll see that on the key. Number 12 here is asking you to do the equilibrium constant, and remember that once you get delta G is negative RT ln K. That means that if we solve that for K, K is equal to E to the negative delta G divided by RT. And so you could figure out what that is. Since we are working at 298, we can use the delta G sub F in this case. So we'll do one of those. Delta G is sum of delta G sub F products minus sum of delta G sub F reactants. We do multiply those by the number of moles, so I'll write N and M for that. So delta G is going to be we've got iron, which is 0. Just write that above it. And we've got carbon dioxide, which is negative 394.4. And then product-wise, reactant-wise, we have Fe2O3. We only have one of those, so that's going to be 1 times negative 742.2, and you have to be careful here not to cross your lines. And then we've got 3 carbon monoxides, so it will be 3 times negative 137.2 for that. So the products term is going to be about negative 1200. The reactants term is going to be about, let's see, the 3 carbon monoxide is going to be about negative 400. So about a negative 1140. So maybe this is going to be somewhere around negative 60 when it's all said and done. Let's see. So parentheses 3 times 394.4, which is negative, minus 742.2 minus parentheses 3 times 137.2, which is negative, and that all comes out to be negative 1500 is what I'm getting there. Did I leave a negative out or something here? I did. What I did was sorry, that's wrong. That's totally wrong. Let's say I forgot this negative sign. cancels out these negative signs. So I've got to do that over again. All right, let's try that again. That's where my estimate helps me out, that I know that that had to be way off. 394.4 negative. Okay, so that first term is negative 1183.2. And then I'm subtracting from that let's try that again. 3 times 137.2 negative equals minus 742.2. Okay, so this term is negative 1153.8. So so that comes out to be negative 29.4. That's kilojoules per mole. That's not our answer, and thankfully it's not one of the possible answers we have over there. What we're going to do is we're going to convert that to negative 29,400 joules per mole, and we're going to take that and put it in that equation there. R here is going to be 8.314 joules per mole, and T here is going to be 298 Kelvin. It's joules per mole Kelvin. So Kelvins cancel out, joules per mole will cancel out there. So when we plug those numbers in, we're going to have, let's see here, 29,400 divided by 8.314 divided by 298. So we've got e to the negative something like 11.87, and that value is going to be, I get 7.0 times 10 to the negative 6 is the value I get for that equilibrium, which is answer B. So we can relate that. 13 is just going backwards from that. We say delta G equals negative RT ln K, again negative 8.314 joules per mole Kelvin. That's our gas constant value times the temperature. So we have 453 degrees C. We add 273 to that to convert it to Kelvin. So 6, 2, carry the 1, 726 Kelvin. That's probably one of the wrong answers, is not doing that. And the natural log of our K, which is 0.020. So what we can do before we start this off is that we can recognize that this is less than 1. And when K is less than 1, that means delta G is going to be greater than 0, right? Because the reactant favors the delta G favors the reactants, not the products. Kind of hard to estimate it, so I'm not going to estimate the natural log of 0.020 for you. But when we plug the numbers in, we wind up with a value of 23,612, 613 joules per mole, or positive 23.6 kilojoules per mole. So I'm going to go with A, with 24 kilojoules for the answer of this one. So again, you have to convert the joules here to kilojoules. You had to convert the Celsius to Kelvin in this case. So just a couple of little places you can mess up on there on that problem. Okay, so I'll skip 14, leave that one too, so you can see that on the quiz. But that's some thermo examples. Again, I don't think anything there is terribly difficult. I think it's a very doable set of material for you at this point. So I hope that you will do those homework problems and clean up on the exam when we get to the exam on this.